Hello, in this video I will be presenting an overview of our work, exploring adversarial robustness of multi-sensor perception systems in self-driving. Several different kinds of sensory inputs are available for today's self-driving vehicles, and each different sensor can complement one another. Thus, many recent works have shown processing image inputs in addition to LiDAR can improve perception. However, images have been found extremely vulnerable to adversarial attacks when processed in isolation, yet there are limited studies on the robustness of such multisensory models that also incorporate images. In this work, we consider a physically realizable object insertion attack by adding a textured adversarial mesh onto the rooftop of host vehicles to full state-of-the-art detection models. To enhance the fidelity of simulation, we first fit a mesh onto the host vehicle's point cloud and use the center of the roof and vehicle heading to determine the exact placement pose for the adversary. Next, we handle occlusion in the LiDAR and image inputs. Finally, we approximate environment lighting with the directional lighting model from the sun. To learn an adversarial mesh, we simulate the adversary into the LiDAR and image modalities in a differentiable manner so that gradients can flow from pixels and LiDAR points back into the mesh parameters. Features from the images and LiDAR are first extracted independently and then fused together by projecting image features into 3D. We then apply an adversarial loss to the outputs to generate false negatives by making the host vehicle disappear and generate false positives by making the model hallucinate bounding boxes. Our experiments evaluate the attack on the false negative, false positive, and overall success rates across the entire test set. Finally, we perform attacks in which we target the LiDAR or image branches in isolation by disabling backward gradient flow in the other branch. Our empirical results show that adding the image stream enhances the robustness of models to LiDAR-only attacks. However, when the attack also targets the image branch, the attack becomes much stronger as we find that the image branch is much more vulnerable to adversarial attacks. Here are some qualitative examples for false negatives. Notice the addition of the adversary in the LiDAR and image inputs, which causes the detection output to disappear for the host vehicle. Here is a video demonstration of the attack. Notice the flickering of the bounding box output in the perturbed snippet. Here is a demonstration of the attack on the Zenith dataset. Here are some examples of false positives. We showed the detection in bird's eye view since far away bounding boxes are difficult to see in the image. Interestingly, we find that due to the projection of image features into 3D during sensor fusion, our attacks are able to generate false positives in distant regions. We further demonstrate this by visualizing the image features in the image plane and after projection into 3D. Finally, we apply several defense methods. Overall, we are successful in defending against almost all false negative examples. However, we find that adversarial defenses still struggle to defend against false positives. We provide more analysis on this finding as well as insights for future work in our paper. Thanks for watching.